Assalamu alaikum warahmatullah. Hello guys, today we will talk about chapter 8, optimization for training deep models. Let's get started. Okay, let me to play. So I have prepared slides and we will talk about these slides. And optimization is generally a very difficult topic. It's very challenging, and yet in deep learning we are still using optimization techniques which are created back in 1980s. So here's my short overview of the chapter. So let's go. First of all, let's talk about what's the difference between pure optimization and optimization in deep models, deep learning. Because in deep learning, our goal is to optimize our network and then apply it to the test dataset in order to have good generalization error. Our goal is not to optimize the training set. Our goal is to make sure that our model works good and it has less and low generalization error. So optimization algorithms that use entire dataset as ones are called as batch or deterministic gradient methods. And in other hand, if optimization algorithm use single example from the dataset for optimization, we call them as stochastic or online methods. And most of users many deep learning networks uses between. They use more than one examples and fewer than all training examples, and we call this kind of usage as mini batch. So mini batch means like mini batch, and it represents the entire dataset, but it is not entire dataset. Randomly selects certain numbers, so we call them mini batch. And neural networks has challenges. There are many different challenges, and one of them is ill conditioning. Ill conditioning is a phenomenon where small changes in the input leads to large changes in the output, which means instability in the model. So ill conditioning can manifest by causing this stochastic gradient descent to get stuck, in the sense that even a very small steps increase the cost function, whereas small steps should decrease, or it should cause small changes. Ill conditioning is one of them. Second problem is local minima. So usually neural networks are non-convex optimization. They belong to non-convex optimization problems. And of course, in convex optimization, which you can see as quadratic function, is convex optimization. In that optimization, any local minima is guaranteed to be a global minimum, which makes our task much more easier optimization. But in fact, neural networks belongs to non-convex, which means that there are plenty and usually infinite number of local minima in that network. And experts suspect that for sufficiently large neural networks, most local minima have a low cost function value, and that it is not important to find a true global minimum, rather than to find a point in parameter space that has a low but not minimal cost. So as you can imagine, that neural networks belong to non-convex optimization function, and in that non-convex there are many infinite number of local minimums, and finding the global minimum is very challenging thing. And experts believe that we don't need to find that exactly the minimum, global minimum we can just minimize the parameter space or just go to minimum number, which we can. So local minima, finding local minima is another challenge. Let's go to next challenge. Plateaus, saddle points, and other flat regions. In non-convex functions or optimizations, they are tough because you have special kind of points or areas where gradient is 0, but it is not necessarily minimum or maximum points. We call them saddle points. And Hessian matrix at saddle points has a mixture of positive and negative eigenvalues. Imagine that a sign of each eigenvalue is generated by flipping a coin. In a single dimension, it is easy to obtain local minimum by tossing a coin and getting heads once. In n-dimensional space, it is exponentially unlikely that all n coin losses will be head. And there might also be wide flat regions of constant value. In these locations, the gradient and Hessian are all 0. Such degenerate locations pose major problem for all numerical optimization algorithms. So here, another challenge is that in optimization, our gradient can stack at saddle points or can get stuck in flat regions which are actually not minimum which we want. So that kind of special regions, we call them saddle points. And Hessian matrix can help us to find whether this location, whether this point belongs to saddle or not. And here it's saying that if the Hessian matrix has both positive and negative eigenvalues, it means we are in saddle point. And here there is a very good example saying that assume that flipping a coin is kind of assume that flipping a coin is like eigenvalues, is sign of eigenvalues, and if you flip n times, and it is unlikely that you will get always the same results, the same heads, which means that it is difficult to find local minima because it is very, very unlikely. The probability becomes less and less and less. Another problem is exploding gradients and cliffs. Neural networks with many layers often have extremely steep regions resembling this cliff you can see in the image, and this results from the multiplication of several large weights together. On the face of extreme steep cliff structure, the gradient updates step can move the parameters extremely far, usually jumping off the cliff structure altogether. So you can see here the graph where, because of multiplication of several large weights and because the neural network has many layers, it will cause to have a big number, big cost function, and in that big number, what will be is that our gradient will jump out of the box, will jump out of the cliff. That's another problem. We call them is exploding gradients, when the gradients becomes very large. Let's talk another problem. There are plenty of different challenges. And next problem is long-term dependencies. So it is about when neural networks have many computational graphs, and their computational graphs are extremely deep, it will cause usually for two big problems. First is vanishing and exploding gradients. We talked about exploding gradients. It's that when very large numbers will come together, it will cause even to big larger number, and it will cause to instability, and that gradient will go out of the box. In vanishing is that when you will multiply very small numbers, for example 0.001 to 0.0 something something 1, and it will cause to very small number which will kind of vanish, which will kind of force the gradient to vanish. That's two challenges in neural network optimization. Inexact gradient. So here it's saying that most optimization algorithms are designed with the assumption that we have access to exact gradient or Hessian matrix. In practice, we usually have only a noisy or even biased estimate of these quantities. Nearly every deep learning algorithm relies on sampling-based estimate, at least insofar as using a mini batch of training examples to compute the gradient. So that, as I told you before, that we usually use mini batch, and in a mini batch we create this sample dataset from our actual dataset, and we are having this assumption, which are not exact gradients, but we believe that this can be representative of the exact gradient. Why we are doing this kind of sampling is because to have a computationally efficient optimization process. And last problem, I think maybe last but not least, poor correspondence between local and global structure. Much of research into the difficulties of optimizations focused on whether training arrives at a global minimum, a local minimum, or a saddle point. But in practice, neural networks don't arrive at critical points at any. Indeed, such critical points don't even necessarily exist. Gradient-based optimization algorithms, like a gradient descent, can sometimes get stuck in these local minimas, mountains, because they rely on a local gradient information to update parameters. If the algorithm reaches a point where the gradients are very small, it might not move further towards the global minimum. So it's another problem that, for example, I think you can see my graph. So here, when we initialize, give the initial point to our parameters, weights, and if they will start from wrong direction of the mountain of the graph, for example in left side, they will think that this is local minimum. But in action, we need to go to the right side, which is global minimum. And many researchers are saying that this is representation, just a hypothesis, and in practice, neural networks don't have that kind of points at all. Maybe scientists are saying like that. And yeah, the fact is that networks, gradients, when optimizing, they can stuck in this mountain place and don't just update and get stuck in this location. That's about challenges. And last, theoretical limits of optimization. So in the context of neural network training, we usually don't care about finding the exact minimum of the function, but seek only to reduce its value sufficiently to obtain good generalization error. That's important. Theoretical analysis of whether an optimization algorithm can accomplish this goal is extremely difficult. Developing more realistic bounds of the performance of optimization algorithms therefore remains an important goal for machine learning research. So here is that optimization is difficult, extremely difficult task, and developing good algorithms is still active research field for machine learning researchers. And what we are doing in practice is that we don't need to find exact minimum, as I mentioned before. We just need to reduce its value to get good generalization error, because our goal in deep learning is not to have good model for our training set. We should have good model which will perform good on unseen data. So that's the difference between our deep learning approach of optimization and pure optimization. That's about challenges. And now let's go about algorithms which we are using nowadays as optimization of gradients. So let's talk about stochastic gradient descent, momentum, and Nesterov momentum. So here is that in stochastic gradient descent we are using mini batch thing, and we are getting sample from the training set, and we are using that sample and we compute gradient descent and we apply the gradient descent, and we will go this iteration until maybe normalization of early stopping occurs or some kind of another criteria occurs. That's how stochastic gradient descent works. Next thing is momentum. So people said, let's add to stochastic gradient descent this momentum thing. So if you look to algorithm 8.2, we add here alpha of momentum parameter. So here, in order to update the gradient, in order to update the weight, we are using also this momentum, and you can see that momentum is affected by the initial velocity and the momentum parameter alpha, which means that our next update of weight parameters depends on the learning rate plus on momentum parameter alpha. And there is also another algorithm of Nesterov momentum. In Nesterov momentum, we also add here interim update. So here basically the update occurs before. We create this interim update of the parameter, and we add this to compute the gradient, and then we update we calculate the velocity, and then we update the actual parameters. So here is what's happening is that this for loop, and instead of getting all parameters, instead of getting all training set, we are sampling it, and we are using this sample to compute to update the parameters. And in action, in practice, it works. And we can enhance this algorithm by adding this momentum or Nesterov momentum. So let's talk about parameter initialization strategies. It is also very crucial for optimization because training deep models is a sufficiently difficult task that most algorithms are strongly affected by the choice of initialization. The initial point can determine whether the algorithm converges at all, with some initial points being so unstable that the algorithm encounters numerical difficulties and fails altogether. Initial point is very crucial for our optimization to perform well. And actually there is no guidance, specific or good guidance of how to select the initial points. General approach is to select small positive number. And another crucial thing is that we need to break symmetry. We should pay attention of breaking symmetry. So breaking symmetry means that when we initialize the parameters in the beginning of the network, and when we start the optimization, we should make sure that when we are updating these parameters, they are not symmetrical with each other. So which means we shouldn't give initial points to each layer weights the same parameters. We should give like different parameters in order to break this symmetry. Why we don't like this symmetry? Because this symmetry kind of blocks the model to update well, to perform training well. Again, optimization is, how can I say, difficult, and it is not yet well discovered. Let's talk about another algorithms which are much more better compared to stochastic gradient descent, but for some models, of course, but for some models they are not good. So let's talk about first algorithm. It is ADA-grade, adaptive gradient, if I don't mistake, we call it like that. And in here is that they are saying that in stochastic gradient or in other optimization algorithms, our learning rate is static. It's the same. For example, if we do 1000 iterations of epochs, it's the same learning rate. And as you know, learning rate affects how big steps we make, how small steps we make. And in ADA grade, what we are doing is that we are changing the learning rate with respect to the largest partial derivative of the loss. And for example, we can change the learning rate to small or to big based on these loss functions largest partial derivative. And for some models it helps very well, but for some it's not good. And let's talk about next algorithm. It is RMS prop. It is modified version of ADA grade with exponential weighted moving average. So this RMS prop is developed for non-convex functions, specifically for neural networks, and they use this exponential weighted moving average instead of the largest partial derivative. And by using this model is also like one of the popular models. And next one is ADAM, adaptive moments. It is combination of this RMS prop plus momentum from the stochastic gradient descent. So the most popular optimization algorithms are stochastic gradient descent, classical, and stochastic gradient descent with momentum, and ADAM, and etc. And these are like common. And you know, people just usually use this ADAM because for people, for researchers, for practitioners, it's important to build good model architecture rather than using good optimization algorithm. Let's talk about another very important and yet challenging topic because of computational burden, about approximate second order methods. So let's talk about Newton's method. So as we know, gradient descent is iterative process of optimization, which we do is this iterative process to find the minimum. But if we use Newton's method, and if our Hessian matrix eigenvalues are positive, we can get benefit from Newton's method and jump directly to the minimum without any iterations, just go directly to the minimum. So our goal is in deep learning, also in optimization, to go to minimum, right? So we can directly jump to the minimum by using Newton's method, only if Hessian matrix eigenvalues are positive. But in reality, in deep learning is non-convex, and in non-convex there are many saddle points, and not always Hessian matrix has positive eigenvalues. Usually Hessian matrix has both positive and negative values, which makes Newton's method bad for deep learning, because Newton's method can cause update to move in the wrong direction, which we don't want initially. And however, we can solve this kind of problems by using some kind of iteration or by using some kind of regularization terms. Yes, and there is another problem with Newton's method, is that Newton's method creates significant computational burden, because it deals with this computation of this Hessian matrix and computation of this Newton's method, and we should care about this big matrix to find this local minimum or global minimum. And that minimum is that in practice we don't necessarily need, in deep learning we don't necessarily need to find this minimum. So but yet the idea is that Newton's method can directly jump to minimum is very how can I say, important, and may change the direction of optimization algorithms also. But yet it is computationally expensive. And let's talk about optimization strategies and meta algorithms. The most recently exciting innovation is batch normalization. Batch normalization is that it's also used for optimization strategies, and where we don't need to change optimization strategy. We need to change the input data to the layers. So here in batch normalization, we are referring to the inputs, where we modify these inputs between 0 and 1 or -1 and 1, where we normalize these inputs in order to reduce this internal covariate shift and to stabilize this learning process and to make networks less sensitive to the initial starting parameters. So we can apply this batch normalization to the first layer, to any layer between, or to the output layer. And they are very, very useful, and people use it a lot nowadays. And yeah, it can be applied to any layer. And this batch normalization can help to have stable learning, because we normalize these big numbers or whatever to a very small range of 0 and 1 or -1 and 1, which makes computation much more easier and stable. But yet it may cause also to vanishing gradient, but not necessarily to the exploding gradient. That's about batch normalization. Let's go to next one, is supervised pre-training. There is one example of supervised pre-training. It is FitNets. FitNets begins by training a network that has a low enough depth and great enough width to be easy to train. So this network becomes a teacher for a second network designed as a student. The student network is much deeper and thinner, 11 to 19 layers, and would be difficult to train with stochastic gradient descent under normal circumstances. So here, what will happen is that student will learn the task, and student will also predict the teacher's inner weights, which automatically improves the student's optimization learning process, and that student will get some kind of hints from teachers from this penalty that students should predict the teacher's hidden weights. So that's logic. This comes from how humans study, right? So if you want to study something, you need to go to teacher. So student and teacher. And student will study, and student will follow the requirements of the teacher or tasks of teacher. So here in deep networks, we can also build such kind of networks, and they are, they are good, and we call it knowledge distillation or dark knowledge. So that's briefly about that supervised pre-training. And lastly, let's talk about designing models to aid optimization. In practice, it's more important to choose a model family that's easy to optimize than to use a powerful optimization algorithms. That's what we are doing now. Scientists who now are trying to build this kind of model architectures, which are good and friendly with current optimization algorithms. And people are doing research to find these good architectures to apply to this stochastic gradient descent, or to apply to this ADAM or another optimization algorithms. Most of the advances in neural networks learning over the past 30 years have been obtained by changing the model family rather than changing the optimization procedure. That's right. And stochastic gradient descent with momentum, which was used to train neural networks in 1980s, remains in use in modern state-of-the-art neural network applications. And optimization strategies and meta-algorithms, continuation methods, and curriculum learning. Continuation method is solving an easy problem, then find the solution to solve incrementally harder problems until we arrive at solution to the true underlying problem. So which means that, for example, if we want to study algebra, we need first to study mathematics, and then by slow go to the algebra, right? And the same, we are thinking that in deep learning, continuation method is that we will give to the model easy tasks to do, and it will use its own weights and biases in order to do next a bit harder task, and by improving these iterations, it will finally reach to the underlying problem, to solve the underlying problem. So building this architecture, this algorithm might be difficult, but it seems very promising, and I think people now actually using that. And there is another curriculum learning, is based on the idea of planning a learning process to begin by learning simple concepts and progress to learning more complex concepts that depends on these simple concepts. So curriculum learning is part of continuation method. So how students work is that they have curriculum, syllabus, and they follow this curriculum, and then they will do complex tasks. But initially they cannot do these complex tasks. And curriculum learning was also verified as being consistent with the way in which humans teach. Teachers start by showing easier and more prototypical examples, and then help the learner define the decision surface with the less obvious cases. So curriculum learning is kind of inspired from how humans work, how humans study, and that's also one of the methods for learning and optimize deep neural networks. So that's it for today. Thank you very much for your time. If you have any questions, ask in comments. That's briefly about chapter 8 of optimization deep models. And I think you get this grasp of ideas and where the optimization strategies and this development is going on. And yeah, I still recommend you to read the chapter 8. You can check deeplearningbook.org. And yeah, happy learning, happy coding. Bye bye.